This tutorial will describe how to use voltage-dependent spiking chemical synapses in your projects. One of the most well-known voltage-dependent channels is NMDA. This ion channel needs the neurotransmitter glutamate to be bound to it and a depolarization of the membrane before it will allow current to flow. This allows NMDA to act as a coincidence detector. Simply having the presynaptic neuron firing and releasing transmitter is not enough to cause current to flow in this channel. It must also be paired with the depolarization that typically occurs when the postsynaptic neuron also spikes. This allows the channel to know when both the pre- and postsynaptic neurons are firing at roughly the same time. This type of information is very important for learning, and we'll be using this type of synapse extensively in the tutorials on learning and memory. NMDA is able to act as a coincidence detector because it has a magnesium ion that plugs the hole of the ion channel and prevents calcium ions from flowing into the cell. When glutamate binds to the channel, it changes the conformation, but the magnesium ion still keeps it blocked. When the membrane becomes depolarized, the magnesium ion is forced out of the hole, and this allows calcium ions to flow into the cell. Let's begin this tutorial by creating a new project. And adding a new organism. Then we'll open the behavioral editor and add 2 spiking neurons. Now let's draw a synaptic connection between them and select the NMDA spiking chemical synapse. Voltage dependence is modeled as a linear increase of the synaptic conductance that's controlled by the postsynaptic membrane voltage. When the membrane voltage is below the threshold potential value, then the conductance is set to the baseline value. This is the regular synaptic conductance that you specify for all chemical synapses. If the membrane voltage is greater than the saturate potential, then the conductance is set to the maximum relative conductance. In between these two, conductance increases linearly between the 2 points. Now let's add a tonic stimulus to neuron 1. Have it start at 50 milliseconds, end at 60 milliseconds, and set the amplitude to 30 nanoamps. Then let's create a line chart to view the membrane voltage of our 2 neurons. Set its end time to 200 milliseconds. Set the collect data interval to 0.2 milliseconds to match the time step of the neural simulation. Then let's run the simulation. Neuron 1 produces a single spike and causes a depolarization in neuron 2 with a maximum of around negative 46 millivolts. Let's go back to the NMDA receptor type and change the saturate potential to be negative 40 millivolts. This will mean that the slope of our conductance change will become larger, so we should see an increase in depolarization compared to the previous example. When we run the simulation this time, we now get a maximum depolarization around negative 39 millivolts. This is a difference of 7 millivolts from our change. Next, let's add a stimulus to neuron 2 to slightly depolarize it before the spike in neuron 1. Add a tonic current stimulus and set its start time to 20 milliseconds, end time to 170 milliseconds, and amplitude to 5 nanoamps. This time when we run the simulation, neuron 2 becomes depolarized enough that it produces a spike. Finally, let's see what happens when we hyperpolarize the neuron. Change the amplitude of the stimulus for neuron 2 to negative 5 nanoamps. When we do this, we get a depolarization of around 4 millivolts. When you compare this to the 21 millivolt depolarization without any pre-stimulus, then you can see that this synapse is dependent on the amount of depolarization in the postsynaptic neuron. This tutorial has demonstrated how to use voltage-dependent synapses in your AnimatLab project.